this is module 36 of the course on econometric modeling. I welcome you all. We were discussing module simultaneous equation system in module 35, and I further continue with the discussion on problem of identification in this module, and then further go to the discussion on estimation and inference. So, we first take an example of identification. We reconsider the demand supply model that we had considered in the beginning of module 35, or when we discussed or when we started the discussion on simultaneous equation system. So, this is a demand equation, this is a supply equation. Now, you note that both these equations have one endogenous variable and the same exogenous variable. So, here z is the exogenous variable, p is another endogenous variable, and of course, q is endogenous variable which is on the left hand side. And we have an equilibrium condition which states that q d equals q s equals q. Now, here suppose z is the price of a substitute commodity. So that alpha 2 is greater than 0. This implies that if the price of the substitute commodity increases, then people will basically demand more of this commodity, and some of the demand for that particular commodity will be substituted by the demand for this commodity. On the other hand, beta 2 is expected to be less than 0, because if the prices of that substitute commodity is growing, then it is possible that producers or farmers would start producing this commodity more. So, as a result of which that particular substituted commodity will more, and as a result of which the supply of this commodity will go down. That is why we expect beta 2 to be less than 0. Now, the reduced form is, we actually obtain the reduced form where we express q and p as a function of a constant term, then coefficient, that is basically in terms of the exogenous variable z, and a combination of the error terms, and we denote them by pi 1 1, pi 2 1 v q and pi 1 2, pi 2 2 v p. You note that here again the second subscript refers to the equation, the first subscript refers to the variable. So, there are 6 structural parameters, that is alpha naught, alpha 1, alpha 2, beta naught, beta 1, beta 2, and 4 reduced form coefficients, that is pi 1 1, pi 2 1, pi 1 2, pi 2. So, what happens? It is obvious that there will not be a complete solution for all 6 structural parameters, the system is not identifiable. So, what we need to do, because the order condition is not fulfilled, that is why we are not able to identify the system. Now, suppose the income x rather than z appears in the demand equation, and therefore, the revised model is q equals alpha naught plus alpha 1 p plus alpha 2 x, and this variable x does not appear in the supply equation, while the supply equation has the price of the substitute commodity which is not appearing in the demand equation. We are actually we are not repeating the equilibrium condition, instead writing q for both the equations, right. So, the structure is now q p equals 1 1 minus alpha 1 minus beta 1. Essentially, I am writing this entire thing in terms of matrix form. Now, this structure fulfills the order condition that the number of exogenous variables that appear elsewhere in the equation system must be at least as large as the number of endogenous variables in the equation. So, the system is just identified, because you can see that for both the equations what we have, one exogenous variable which appears here, but does not appear here, and one endogenous variable. Similarly, one exogenous variable which appears here, but not here, and one endogenous variable. So, that is why the system is just identifiable. The reduced form is in terms of matrix form, we write it like this, where delta is alpha 1 minus beta 1, which is essentially the determinant of this matrix. And the unique solution for the structural parameters in terms of the reduced form parameters now can certainly be obtained. So, we can see that we have values of alpha naught, alpha 1, alpha 2, beta naught, beta 1, beta 2, all derived in terms of the the reduced form parameters, right. And we have now basically 6 reduced form parameters, 1, 2, 3, 4, 5, 6, fair enough. So, this is how the system becomes just identified. Now we talk about estimation and inference. Now there are two approaches to estimation and inference for simultaneous equations model. The first one is limited information estimators, which are constructed for each equation individually and estimated using least square one equation at a time. So since we are not using all the information that are available with us, we call it limited information estimators. And the second is full information estimators, that are used to estimate all equations simultaneously. So, the complete set of information is being used, and that is why we call it full information estimators. Now, suppose the jth equation is written as yj equals xj beta j plus yj gamma j plus uj. So, the usual thing that we have a set of endogenous variables, the corresponding coefficients denoted by gamma, the exogenous variables, the corresponding coefficients denoted by beta. Now, this is for a particular equation, the jth equation. Now, here xj is the set of exogenous variables that appear in the jth equation. Also say x denotes the set of all exogenous variables and xj star denotes the set of exogenous variables that are not in equation j. So, this consists of all those variables or all those exogenous variables which do not appear in the jth equation, fair enough. Therefore, my x will consist of one xj and one xj star, which implies that the total exogenous variable is actually divided into two components, one which appears in the jth equation, the other one which does not appear in the jth equation. Now, we are writing this entire thing, that is the set of exogenous as well as endogenous variables as zj, and all the coefficients, that is beta j and gamma j, taken together as delta j, and uj is as usual. So, equation 1 cannot be estimated using OLS as it is inconsistent due to the correlation between yj and uj. The usual approach will be two-stage least square using instrumental variables. So, we used instrumental variables in certain situations. So, one such situation was when we expect that the some of the exogenous variables are actually correlated with the error term. So, this is a situation where some of the variables we do not expect, we know that they are correlated with the error term. So, we need to use some instrumental variables. In this setting, the instruments come from elsewhere in the model, that is the variables that are not in the jth equation can be utilized to come up with or to form the instrumental variables. Thus, for estimating the linear simultaneous equations model, the most common estimator denoted by delta j hat 2 SLS, you note that j refers to the jth equation and 2 SLS refers to the fact that this is an instrumental variable estimation. And what we obtain is zj hat prime, zj hat whole inverse, this is actually zj, zj hat prime zj whole inverse zj hat prime yj. So, what is this? This is actually, now when I expand it, the whole inverse thing is basically zj prime x prime x inverse x prime zj. Well, where basically this implies that zj hat are obtained as predictions in a regression of the corresponding column of zj on x. So, zj consists of all the exogenous as well as endogenous variables that is there in the jth equation, and x consists of all the exogenous variables only. Now, I am running a regression of zj on x, that is all the exogenous and endogenous variables appearing in the jth equation on all the exogenous variables, and the predicted values so obtained is denoted by zj hat. Okay. And then this zj hat is utilized in order to arrive at the 2 SLS parameter, and similarly we have this thing. So, as you can see that zj hat is equal to zj prime x into x prime x inverse x prime. okay. That multiplied by yj gives me this component, and the rest we have in the inverted term. Note that we are predicting zj equals xj yj using x equals xj xj star. So, in order for the predictions to be linearly independent, there must be at least as many variables used to compute the predictions as there are variables being predicted. So, when we compare xj yj with xj xj star, we see that there must be at least as many variables in xj star as there in yj in order for them to be linearly independent. So, this is exactly the order condition. The practical rule of thumb that every equation have at least one variable in it that does not appear in other equation will guarantee this outcome, right. So, two-stage least squares is used nearly universally in estimation of simultaneous equations model. However, some applications have suggested that the limited information maximum likelihood estimator based on the normal distribution may have better properties. Now, I am not going to discuss limited information maximum likelihood method or technique here in detail, because that is sort of outside the purview or scope of this course. This is basic course. Instead, I just discuss certain properties of the LIML, that is limited information likelihood maximum likelihood method. What are the advantages it has over 2SLS if we can go for LIML. So, a result that emerges from the derivation is that the LIML estimator has the same asymptotic distribution as the 2SLS estimator, and the latter, that is the 2SLS estimator, does not rely on an assumption of normality. However, one significant virtue of LIML is its invariance to the normalization of the equation. So, whenever we go for any kind of normalization, first of all, LIML results do not change with that. So, we give an example that for example, we consider this equation and the same equation actually written by while taking y2 to the left hand side. So, when we take y2 to the left hand side and bring y1 to the right hand side, then in order to make its coefficient equal to 1, we basically divide the entire equation by gamma 2. So, the 2SLS estimator is not invariant to the normalization of the equation, which implies that 2SLS would produce numerically different answers. However, LIML would give the same numerical solutions to both estimated problems. So, this is an advantage of LIML over 2SLS. And the second virtue is that LIML's better performance in the presence of weak instruments. Overall, though the large sample properties of all estimators, that is 2SLS, OLS, LIML and so on, are the same, some evidence favors LIML when the sample size is small or moderate and the number of over identifying restrictions is relatively very large. Then it is possibly observed that LIML gives us better results. Now, we consider system method of estimation, that is full information estimation technique. So, let us formulate the full system of equations first of all as y1 y2 to ym is the vector of all the m variables for all the t time periods, and then we have z1 z2 zm basically consisting of all the endogenous and exogenous variables corresponding to a particular equation. So, we have y1 equals z1 delta 1 plus u1, the rest all are 0. Similarly, y2 equals to z2 delta 2 plus u2, which implies that we are having one endogenous variable to the left hand side, rest of the endogenous variables are taken to the right hand side, clubbed with the exogenous variables we are denoting them by z, and we are denoting the coefficient matrix as delta. Alternatively, we write it as y equals z delta plus u, where expected value of u conditional upon x is equals to 0 and expected value of u prime u, that is the variance of x conditional upon x, is denoted by sigma bar, where sigma bar is equal to sigma Kronecker product I. Kronecker product I essentially implies that each and every element of sigma is multiplied by an identity matrix I. Now, the three IB techniques that are generally used for joint estimation of the entire system of equations are 3-stage least square or 3-SLS, generalized methods of moments or GMM, and full information maximum likelihood method or FIML. We will only discuss 3-SLS here because generalized method of moments and FIML, not only there is time and space constraint, but also they are much more complex estimation techniques and outside the purview of this course. So, for equation 2, the least square estimator, this is my equation 2, right. This is equation 2 and its least square estimator. If you remember, the OLS estimators are x prime x inverse x prime y. So, by drawing analogy, my OLS estimators here will be z prime z inverse z prime y. So, we denote delta hat, the estimated OLS parameters, by z prime z inverse z prime y. This is equation by equation ordinary least squares and is inconsistent and inefficient. It is inconsistent because as you can see that z consists of endogenous variables and z and u are correlated, but still we are going ahead with OLS. So, that is why it is inconsistent, and previously we have also discussed that the system as a whole will produce inefficient estimators. Now, this is inefficient compared with estimator that makes use of the cross equation correlations of the disturbances. For the first issue, we turn once again to an IB estimator. So, by considering instrumental variable estimation technique, we will be first taking care of the inconsistency problem, and the problem of inefficiency will be taken care of by using a generalized least square approach, which also earlier discussed in the context of heteroscedasticity or serial correlation. So, the IB estimator is delta denoted by delta IB. So, first we had delta hat, then we have delta hat IB, which is actually the 2-SLS estimator in this context, and this is actually z hat prime z inverse z hat prime y. This is simply equation by equation 2-SLS and it is a consistent estimator. Now, where you can see that z hat is basically consist of the instrumental variables which have been obtained from a regression of zj on the x's. This has already been mentioned earlier, that now we are, instead of having z1, z2, we are having z1 hat, z2 hat and so on. So, these are basically instrumental variables, and the instrumental variables are obtained as x prime x into x prime x inverse x prime z j, which implies that we are running a regression of zg on the x's, where j stands for I equals to 1 to m. However, we would expect this estimator to be less efficient than a GLS estimator. So, our natural candidate would be to go for a third stage. So, that is how we have a 3-SLS, that is the third one is denoted by delta hat 3-SLS, which is basically delta hat IV, and we are applying GLS on it. If you remember, when applying GLS, what we used to do is that in order to convert the error term to an error with constant variance, we would be dividing the entire equation or all the data by the non-constant component of the error term. So, here the error variance is sigma Kronecker product I. Now, we are basically dividing this estimator, the initial estimator, or rather the least the IB estimator z hat prime z whole inverse z hat prime y. This entire, first of all, z hat prime z whole inverse is now intercepted by including a sigma inverse Kronecker product I. This implies that we are basically dividing each element of this z hat prime z inverse by the non-constant component of the error variance. And similarly, z hat prime y is also divided by the non-constant component of the error variance. That is why we are also having a sigma inverse chronic product I here. Now, expanding the expression, we will obtain delta 3 SLS as this basically refers to the first component. So, this is corresponding to the first or left hand side. Okay. So, we have sigma 11 Z1 prime Z1 and so on, and this actually corresponds to the right hand side, that is Z hat prime sigma inverse chronic product I y, if expanded would take a form like this. So, this is my delta hat 3 SLS or delta hat IV 2 SLS or GLS. Now, two conditions are required for this estimator to be a valid estimator. The first condition is that P lim upon T Z hat prime sigma inverse chronic product I multiplied by U is equals to 0. This is actually m sets of equation, each one of them is of the form probability limit 1 upon T summation j equals 1 to m sigma I j z I hat prime u j equals to 0 for each and every I equals to 1 to m. Now, you can ideally this implies that the instruments that we obtain, that must be uncorrelated with the error term. And the second condition is that this term, that is this term actually should be invertible. So, this says that this term should be not equal to 0 and the matrix be non-singular. If these two conditions are fulfilled, then we can always obtain these 3 SLS estimators. Okay, so finally, the steps involved in these 3 SLS estimators are, first of all, estimate pi by ordinary least squares and compute yj hat for each equation. Then we compute delta j to SLS hat for each equation and obtain this estimated value of sigma ij, that is the components of the sigma matrix, covariance variance matrix, and this is simply yi zi delta I hat whole prime yi zi delta I hat multiplied and then divided by t. So, the the numerator you can see from this expression, from this equation you can see that if I take z delta to the left hand side, then we will be left with u. So, this implies that this is ui hat multiplied by ui, that is divided by t, giving us the variance of the error term associated with the ith observation. And then compute the GLS or delta 3 SLS hat and an estimate of the asymptotic covariance matrix using z hat and sigma hat. So, that broadly about simultaneous equation system. How do we tend to identify them? What are the methods of estimation and inferences that we generally go for? Now, most often these simultaneous equation systems which are driven by structural assumptions require a lot of theoretical implications in order to make the system identifiable, and most often when the system is identifiable, then standard statistical packages can run this kind of regressions in order to produce the estimated values. These are the references I have primarily used for coming up with the discussion on simultaneous equation systems. Thank you.